Okay, our model, we have weight inversely proportional to the square of the distance from the center of the earth, and that gives us the weight equals k over distance squared, proportionality, the form of our function. W equals k over d squared, or y equals k over x squared, where y is weight, x is distance. If weight is 110 when the distance is 6,400, now 6,400 kilometers in the context of this problem is the radius of the earth, so this would be the weight of this person on the surface of the earth. It would be 110 pounds. Okay? So, what do we get? Well, using this form of the proportionality, weight is 110 when distance is 6,400. We get this, and we solve this for k, obtaining k equals, well, 4.4 billion. So our model is weight equals k over d squared. K is 4.4 billion, so weight equals this number over d squared. And then the question that was asked is, what's the distance if the weight is 65? Well, it means 65 is our weight, and we solve for the distance. So we plug in 65 for the weight, and we get an equation for the distance. We solve it, we get a distance that I estimated to be 8,600, but I did a lot of estimates. I think it turns out to be closer to 83 or 8,400. Okay? So at 8,600 kilometers, the weight of this individual would be down to 65 pounds. Good way to lose weight. Now, not really, because you're not really losing mass, you're losing weight. And there's a distinction there that everybody should be aware of, but we're not going to talk about it. Okay, now, within this context, we want to interpret a graph of this function. So our function is weight equals this over this, or y equals this over x squared. This being our value of k, our 4.4 billion. Okay, well, if we graph this function, the graph is going to look something like this. Now the graph of this expression would go up asymptotically to the y-axis, but the domain of this function is just d greater than 6,400. 6,400 means 6,400 kilometers, and that's the radius of the earth. So for the distance that's less than the radius of the earth, that means we're inside the earth, and this model doesn't apply. It only applies outside, at distances greater than the surface of the earth from the center, meaning, from here on up into space. Okay, so there's our graph. It's very easy. This is just a stretched 1 over x squared graph. So this is like 1 over x squared, vertically stretched by factor 4.4 billion, which is just this number. So we multiply this number by 1 over x squared, we get this. And we can also use w and d for the y and the x, having more meaning weight and distance. Okay. So let's just talk about interpretation and what we mean by interpreting. Meaning of f of 10,000. What's the meaning of f of 10,000? We can see what f of 10,000 is. How do we do that? Well, on the graph, here's 10,000. Okay, between 6,400, 12,800, a little closer to 12,800, and over here we get the weight. Now, according to this graph, that's about 40% of the 110 pounds. Estimate f of 10,000, approximately 44. Now we could plug 10,000 into this function, and actually we would get 44. That was an honest estimate. I just accidentally got the right number. And we don't expect our estimate to be that close, but I just took that as 40%, and that's what we came out with. Okay, so here's 10,000. There's our estimate. Now what's the meaning of that? So the meaning of this is, well, at 10,000 kilometers, from the center of the earth, 110-pound person, and more specifically, we could say a person who weighs 110 pounds at the surface of the earth, but that's what we mean by 110-pound person. Weighs 44 pounds. Not a good way to lose weight, but of course, it's your mass, not your weight, that determines what you're going to weigh at the surface of the earth, and that's your, what we'd call it, maybe your real weight. Okay, so you notice I've made a statement here. Now, when we interpret graphs, there's a meaning, okay? In the interpretation problems, there's a meaning for this, and there's a meaning for this, and we have to make a statement about what everything means. That's the meaning of f of 10,000. Okay? The solution of f of x equals 100. What's the solution of that? Well, I hope everybody understands that that's what we get if we go to 100 here, project over here, and project back down. And I'm going to say we get about 7,000. Okay? So I don't have room to write that well. Okay, here x equals 7,000. So my estimated solution is x equals 7,000. Of course, I can compare that estimate, and you're asked to often do that, what's the percent difference and all that stuff. But that is the solution, okay? What's that mean? Well, I could say in terms of maybe the objective of weighing less. To weigh 100 pounds, a 110-pound person can go to a position (7,000 kilometers) from the center of the earth. Okay? And we could even extend that, you know, what's that mean? 7,000 kilometers from the center of the earth? Well, I told you that 6,400 kilometers is the radius of the earth. So I can say weight is 100 pounds. If the person goes 600 kilometers high. That is above the surface. Okay? Now, how about a story about the x interval from 7,000 to 8,000? Okay, just in terms of estimates, we don't have to do calculations, but we can, and we could. Well, at 7,000, x equals 7,000, that means we're 7,000 kilometers from the center. Weight appears to be 100. Okay, at 8,000, let's see. 8,000 would be 1,600 plus that would be about a quarter of the distance. You know, and these estimates aren't going to be very good because I'm trying to estimate things that would need to be estimated pretty accurately. So you can do calculations and check me on this. Okay, so I'm thinking that this looks like about, 2/3 of this. So I'm going to say this is about, let's just say my estimate of this is 70. Okay, if this is 100, that could look like 70. Then what can you say about the interval from 7,000 to 8,000? Well, we can say at 7,000 kilometers from the center, weight is 100 pounds. At 8,000 kilometers, weight is 70 pounds. So it looks like the rate of change of weight with respect to distance from the center change in weight divided by the change in the distance equals, what's our change in weight? Well, it's 70 pounds is what we're at, 100 pounds is where we started, and distance is 8,000 kilometers minus 7,000 kilometers. Well, that comes out negative 30 over 1,000. And that looks like negative 0.03 pounds per kilometer. Okay? That you can also verify, if these estimates are correct, is the slope of this fundamental triangle. Of course, we've got the formula. We could calculate the actual slope and see how good my estimates are. As I say, they aren't going to be very good. But let's just say there's the estimate, okay? What else can we say? Because we're supposed to tell a story about the x interval, right? So the story, simple story, on the average, between 7,000 kilometers and 8,000 kilometers from the center, losing 0.03 pounds per kilometer. It doesn't sound like a lot, but if you go 30 kilometers, you're going to lose a pound. Yeah, pound loss is worth, it's something. Okay. That's the entire idea. Well, not the entire idea, but that's an example of how we interpret a graph. Okay? Now, the interpretations you're asked to do, or you've been asked to do, don't say f of 0 is where the graph meets the x-axis or the y-axis. Or the solution to f of x equals 0 is where the graph meets the x-axis. We know that, and of course you want to say that, but we want that in terms of what the meanings of these things are, not in terms of the generic characteristics of the graph. What is going on with that investment? What's going on with that plant spacing? What's going on with whatever the interpretation is? And we want to get good at that, because that's going to connect the mathematics that we're learning in this course, and we will have learned within 2 weeks, I certainly hope, because that's when the finals due, that we will have learned in this course with the real world and with things that you might be doing in your career and in your life.